Could you believe beneath this ocean, a bullet train is passing through solid rocks? This shouldn't exist. The engineers said it was impossible. The geology said it was suicide. 34 workers proved both of them wrong with their lives. This is the Seikan Tunnel, 53 kilometers of reinforced concrete carved through volcanic rocks beneath the Pacific Ocean, the deepest undersea tunnel ever built by human hands. And this is exactly what it cost to build it. It took 24 years to build, cost $7 billion. 34 workers never came home. And it still leaks seawater every single day. But why did Japan risk all of this in the first place? Because in 1954, Typhoon Marie hit the Tsugaru Strait. One night, 1,430 people drowned. Japan looked at that number and made one decision. Never again, so they went under it. And this is exactly what it cost to build it. But mapping a path under the strait revealed a geological profile that shocked every surveyor involved. Early core drilling had to be conducted in freezing winter conditions, fighting unpredictable tides and blinding snowstorms. When the samples finally came up, engineers realized they weren't dealing with solid, predictable granite. Instead, the path ran through a volatile mix of fractured volcanic rock, collapsing mudstone, and saturated sedimentary clay. Worse, the alignment would have to cross 9 separate tectonic fault lines. Under intense geological stress, the entire seabed behaved like a massive stone sponge, completely saturated with high-pressure saltwater. At the tunnel's lowest point, the combined weight of sea and rock above exerted a continuous pressure of 14 bars, 14 kilograms of crushing force on every single square centimeter of exposed rock face. A miscalculated dynamite blast could instantly transform a dry workspace into an uncontrollable flood. Standard mining techniques were completely useless here. Simultaneously, construction teams mobilized on both coastlines, one on the Honshu shore, one on the Hokkaido shore, each beginning the same brutal process of cutting vertical access shafts straight down through the rock toward the tunnel depth. Heavy rotary drilling rigs, crane systems, and underground transport equipment were shipped to both sites, the machinery descending piece by piece down the growing shafts as construction teams on both sides raced toward each other through the dark. Project leaders understood immediately that blasting the main rail tunnel directly into this unknown rock would be catastrophic. They needed a way to test the geology safely before committing the full workforce. The solution was a unique triple tunnel system driven forward in parallel stages. First, crews deployed a narrow vanguard line called the pilot tunnel, just 5 meters wide, driven well ahead of the main path to test the ground blind. Its job was to act as an early warning system, intentionally absorbing the hit from any hidden water hazards before the larger teams arrived. Crews excavated the service tunnel, handling equipment transport, ventilation, and water drainage. Only when both smaller tunnels had successfully stabilized the section could the third phase begin, the excavation of the main rail cavern, the large structural vault built to carry the dual tracks. This interconnected network meant that if a major blowout occurred at the digging face, flooding could be isolated, managed, and pumped away without destroying the entire project. To advance through this environment, standard construction machinery had to be completely redesigned. The heavy, shifting weight of wet volcanic rock would warp standard tunnel shields, pinning equipment permanently underground. The critical tool was the horizontal diamond core drilling rig, custom machines engineered to punch continuous diagnostic test holes hundreds of meters ahead of the blasting face. Their internal drilling rods were sealed within heavy hydraulic packings to withstand the 14-bar external water pressure. When a probe drill breached a hidden fissure, automated gauges instantly measured the pressure and volume of the incoming water. Behind these came multi-boom pneumatic drilling jumbos, drilling precise blast holes into the rock face in minutes. They were paired with automated mucking machines, equipped with steel gathering arms and heavy conveyor tracks, working continuously in cramped, muddy spaces to clear thousands of tons of blasted volcanic rock. Without these mechanical systems reading the ground ahead, the project would have remained an impossible blueprint. Deep under the middle of the strait, excavation teams struck the Matsumai stratum, a volatile layer of loose sand and mud that collapsed the moment it was exposed to atmospheric air. Trying to erect a permanent concrete arch inside ground with the consistency of wet mud was an extraordinary problem. Standard steel arches and timber supports would simply sink under the shifting weight. The engineers had to stabilize the mountain before they could safely dig through it. They developed an industrial chemical injection process, a proprietary mixture combining ultra-fine cement with liquid sodium silicate, a compound known as water glass. This chemical grout was engineered to flash set on contact, binding loose material into solid structure within minutes. Grouting crews drilled a dense radial pattern of deep holes into the soft ground ahead, then pumps forced thousands of gallons of this mixture into the volcanic sponge at a massive 400 bars of pressure. The force drove the grout deep into every microscopic pore, transforming loose, saturated sand into a waterproof barrier of artificial rock. Beneath this chemical shield, construction crews lived with constant physical punishment. The miners at the face worked in a loud, echoing environment hundreds of feet below the ocean floor. The low-frequency creaking of heavy iron support frames served as a continuous reminder of the weight pressing down from above. Air temperature in newly blasted zones regularly hit 40 degrees Celsius, heat radiating directly from the Earth's crust, trapped alongside diesel exhaust and rock dust. Humidity stayed near 90%, causing thick rock dust to stick to workers' skin like paste. Miners worked in short, intense rotations, relying on ice vests strapped to their chests to stave off heat stroke. The constant roar of pneumatic drills and concussive dynamite blasts wore down their hearing over time. Many permanently lost their hearing before 30. Others developed severe lung damage after years of inhaling explosive dust and diesel fumes. The schedule demanded around-the-clock progress, 3 shifts a day, 365 days a year. This was a massive, mostly anonymous workforce, trading their physical health to carve a path through the rock. Despite chemical grouting and predictive drilling, the ocean breached the tunnel defenses multiple times. Without warning, a massive unmapped fault line split open directly in front of the active mining face. High-pressure seawater burst through the rock at 80 tons per minute, roaring like a jet engine in the confined space. The sudden hydraulic force warped heavy steel support frames, turning loose equipment into dangerous debris. Emergency sirens echoed through the dark caverns as workers scrambled onto transport vehicles to escape the rising flood. The command center ordered immediate closure of massive steel bulkhead doors, isolating miles of tunnel to contain the damage. For months, the project's survival was genuinely uncertain, as high-capacity turbine pumps worked continuously just to hold back the water. Specialized salvage teams entered the flooded zones, working entirely by touch in pitch-black water to inject thousands of tons of grout into fractures they could not see. It took nearly 5 months of high-risk engineering triage to plug the breach, drain the sector, and resume digging. To ensure that the Honshu and Hokkaido crews digging toward each other would actually meet, engineers had to completely reinvent surveying precision. The Seikan Tunnel became one of the first major civilian applications for high-precision laser guidance systems. Specialized laser transmitters were anchored to vibration-isolated concrete stations deep along the tunnel walls, projecting concentrated light beams down the center of the expanding caverns. When the final rock barrier in the pilot tunnel was blasted away on January 27, 1983, the world watched. The 2 separate excavations met beneath the middle of the Tsugaru Strait with a horizontal variance of less than a few centimeters. After nearly 2 decades of blind digging through unstable ground, the math had been perfect. With both excavations finally connected, the full 53-kilometer corridor was sealed and lined with structural concrete for the first time. Precast concrete sleeper blocks were positioned along the full tunnel floor, each one set to millimeter precision. Steel rails were bolted directly onto the sleeper blocks, completing the dual-track system that would carry the Shinkansen. Overhead catenary power lines were tensioned above the tracks, the tunnel transforming from a raw excavation into a functioning railway. Deep within its core lie 2 underground stations built directly into the subsea bedrock, Tapikaite on the Honshu side and Yoshioka Kaite on the Hokkaido side. Positioned 150 meters below the ocean floor, deeper than a 40-story skyscraper is tall. These stations were not designed for standard passenger commuting, but as specialized emergency survival hubs. Once docked, high-capacity ventilation fans activate instantly, creating a wall of positive air pressure to force toxic smoke away from evacuation platforms. Blast doors seal passengers into pressurized escape tunnels completely isolated from the incident zone. To connect these deep outposts to the surface, engineers cut emergency shafts containing 2,247 steel steps climbing back toward daylight. Even today, seawater constantly leaks through microscopic fractures in the concrete lining. The entire 53-kilometer alignment is built on a precise incline, forcing all seeping water to flow naturally toward deep collection sumps. Hidden beneath the tracks, massive turbine pumps work around the clock to force that water back into the ocean, permanently, endlessly. Every night, after the final train clears the sector, specialized maintenance locomotives equipped with laser scanners and ultrasonic arrays crawl through the dark at walking speed, checking every millimeter of the structure. The track uses solid precast concrete slab rather than traditional stone ballast because at high speeds, intense air pressure variations inside the tube could loosen ballast stones and turn them into projectiles. Instead, rails are bolted directly onto precision concrete blocks, monitored by fiber optic strain gauges every single millisecond. A high-speed train entering an enclosed tunnel acts like a giant piston, violently compressing the air column ahead of it, creating a pneumatic shock wave that accelerates as it nears the exit portal. Without pressure relief ducts, every train entering the tunnel would fire a compressed air cannon blast out the far end. The solution was elegant. Engineers cut specialized pressure relief cross passages at exact intervals between the twin parallel tunnels. These ducts allow the compressed air wall to expand safely into the adjacent tube, dissipating the shockwave before it reaches the portal. Today, passengers reading or drinking coffee inside the quiet, pressurized cabins are completely insulated from the severe physics occurring just outside the glass. The successful opening of the Seikan line on March 13, 1988, the politicians who cut the ceremonial ribbons did not build this tunnel. That achievement belongs entirely to a generation of Japanese miners who traded their youth to work in the dark. Young men entered these vertical access shafts as apprentices and emerged decades later as grey-haired veterans. 34 workers lost their lives directly to cave-ins, accidental explosions, and water blowouts during the long construction years. The vast majority were never given public medals or recognized outside of dusty engineering archives. They gave their hearing, their lungs, and in some cases their lives, while the surface world moved forward into a modern era of peace. This tunnel was built by anonymous drilling crews who stood knee-deep in freezing saltwater floods. It was built by a society that looked at a major maritime tragedy and chose to engineer a permanent solution. For decades, the weight of the Tsugaru Strait has pressed against this underground void, and the engineering has held. The true cost of infrastructure is never just financial. It is paid in human effort, manual labor, and years of dedicated focus. The Seikan Tunnel remains a quiet working testament to what can be achieved when human intelligence is applied to the most hostile environments on Earth. The ocean continues to wash against the outer concrete shield, but the inner core remains dry, secure, and perfectly aligned. The generation of miners left behind a structural masterpiece built to last a century. A definitive, permanent victory of human ingenuity over the unpredictable forces of the ocean floor.